Okay, well, thank you so much for having me. I would like to very especially thank Stefan for this opportunity, for the talks that I gave last week, and also for this one now. I met Stefan for the first time in a conference in 2004 that I organized with some friends that he mentioned back then. So I'll put this as a conjecture that was formulated at some point, at least before 2004. I don't know exactly when. So this was Stefan Stolz and Peter Teichner were working on trying to find a field theory-based model for elliptic cohomology. And in the context of that, they they were looking for the following. So they conjectured the existence. There exists a three-category, let's call it C, such that, and then they had some number of requirements. So this is a symmetric modular tensor three-category. So there's a tensor object. In particular, there's also a unit object. And one of the things was that if I take the unit object and look at everything from the unit object to itself, well, that's now a two-category. And that should be the same as the two-category of von Neumann algebras. So the objects are von Neumann algebras, the morphisms are bimodules, and then the two morphisms are maps of bimodules. And then another thing that Stefan and Peter really wanted was that, so let me call it pi naught of C cross. C cross is the notation that you use in algebra for units of a ring. So this is the set of invertible objects with respect to the tensor product operation. And pi naught of a, typically you take pi naught of a space, and that means that you identify all points that are connected by a path. And here I want to identify all objects that are connected by an isomorphism. So this is just talking about the set of isomorphism classes of invertible objects. So they wanted this. This has an interesting object of order 24 squared. And this number comes from some known facts about elliptic cohomology. So this is a periodic cohomology theory such that in degree n plus 24 squared, you get the same as in degree n for every n. Okay, so this was very inspiring to me and to my collaborators. So jointly with Arthur Bartels, Chris Douglas, and myself, we came up with a proposal of what this three-category could be. So let's say proposal. And the three-category of conformal nets. And I'll come later to the meaning of all these words. So this is just a little bit of the background story. So we know that this three-category does satisfy the first requirement. So that's good. And then we also have a candidate for this interesting object, but we actually don't know the exact order of that candidate. The candidate is called the free fermion conformal net. The order, we only have a lower bound. We don't know. Sorry. Yes?
So what is this is a group? The pi 0 of C star?
That's right. So C comes with a tensor product. I take invertible objects with respect to the tensor product. That's this cross notation. So by definition, I restrict to the things that form a group. That's right. It's an abelian group. So there's this free fermion conformal net, which is interesting. But there's many more interesting examples of these conformal nets. And a source of examples of conformal nets come from loop groups. So we have loop group nets live inside that 3 category. So then there was the work of Jacob Lurie on the cobordism hypothesis that came to be. And what Jacob says is that if you have an n category, and we're going to be looking at that 3 category of conformal nets, and you have a fully dualizable, symmetric monoidal n category, and you have a fully dualizable object in that n category, you get for free a topological quantum field theory in dimension n. So you assign, so this is a functor that takes manifolds of dimensions between 0 and n and assigns things in this n category. So points go to objects, 1 manifolds go to morphisms, 2 manifolds go to 2 morphisms, and then in this case the top layer will be 3 manifolds that go to 3 morphisms in here. In particular, closed 3 manifolds go to and if you work out what it means to be what you get for a closed 3 manifold, you will get just a number for the 3 manifold. So, so these loop group nets turn out they turn out to be fully dualizable. This is it's not, I only know this fact actually for some of the loop group nets, and this is based on some, so for some other, for type A and D it's known, for other types it's certainly expected but not known. But let me sort of pretend that it's known. So these turn out to be fully dualizable, and then by work of Jacob Lurie on the cobordism hypothesis, we get 3-dimensional TQFTs. For each loop group. We also get one for the free fermion, but that's a very boring one because the free fermion is an invertible object. For example, the 3 manifold invariants that you will get are always going to be always going to be complex numbers of norm 1 in this case. Whereas these numbers that you get, the 3 manifold invariants, are much more interesting. Okay, very good. I believe that coordinate hypothesis, then I get some 3D TQFTs. I don't really know what these 3D TQFTs are, but well, by talking to people, specifically to Jacob, I ended up being convinced that this qualifies to be called Chern-Simons theory. I actually wouldn't know how to justify the fact that it's called Chern-Simons theory. If you talk to physicists and ask them what is Chern-Simons theory, they will say something, and I don't know how to connect that something to this story. So, anyways. So let me spell out the kind of structure that we have here. So if I have a zero-dimensional manifold, for example, a point, then this version of Chern-Simons theory will assign to it, well, just like in an arbitrary n category, you get objects assigned to points. So the objects here are called conformal nets, so we get a conformal net. For the case of the TQFT assigned to a particular loop group net, well, the point goes to that loop group net. If I have a one-dimensional manifold with boundary, that can be viewed as a one morphism in the cobordism category, and it gets a one morphism in the 3 category, and that goes by the name of a defect between conformal nets. If the manifold happens to be closed, then we get a defect between the trivial net and itself. But that is something that I've already told you what that is. If I put here the trivial conformal net and itself, a defect, you don't need to know what a defect is. If you sort of believe that, then you know that it's the same thing as a von Neumann algebra. So we have associated to every closed manifold a von Neumann algebra. So I can go on. So if I have a cobordism between two of those guys, then I will get I won't be very specific here, you get a two morphism between these one morphisms. And the one morphisms, I decided to call them defects. A special case, which is when the one manifold is of that kind. So well, then I get a two morphism between two defects that are of this form, and that is the same thing as a bimodule between von Neumann algebras. So a Hilbert space equipped with two actions. And well, we can go to specialize even more and say what happens if this has no boundary. So here's an example of a two manifold without boundary. So then I need to know what is the algebra associated to the empty one manifold, and that's the algebra of complex numbers. And here I would get a bimodule between C and C, which is to say just a Hilbert space. We're working in a context where things are Hilbert spaces. But it's going to be a finite dimensional Hilbert space. So if you think of it just as a vector space, it's not very, you haven't lost too much. So this wasn't quite the kind of structure that some people expected. So for example, Dan Fried has had a version of Chern-Simons theory that is also expressed in that language, where it's like finite group Chern-Simons theory. And and also there's like, I've been talking to Konstantin Telemann, and what they really wanted is a story that goes as follows. They wanted to have a thing that assigns to a point not a conformal net, but a tensor category. And a thing that assigns to an interval a bimodule category. Well, so this is a category equipped with two actions. So this, if I have two tensor categories, a bimodule category is just a category such that it makes sense to take an object of this guy here and an object of the tensor category and produce a new object here. It's a categorified version of the notion of bimodule. If the tensor categories are trivial, for example, if I'm in this situation, then a bimodule category is just a category. So here I just want a category. Let's go on and fill in this table. One of these guys is going to be a map between bimodule categories. So, well, what's a map is called a functor in this context. So a functor between bimodule categories, and here if your bimodule category happens to be just a category with no actions, then that's just a functor. So that's here, just want a functor. And finally, at the very bottom, if I have a functor from the trivial example of a category is the category of vector spaces. And a functor between vect and vect is always given by tensor with a vector space. So this is, at the end of the day, we just get here a vector space. And so the reason why these guys wanted this as answer is that they had an example, namely Chern-Simons theory for finite groups, also known as Dijkgraaf-Witten theory. And in that example, you associate to a point the category of all G-graded vector spaces. So G is your finite group, so it's just an element in this category consists of one vector space per element of G. And then there's a way of taking the tensor product of two such things. If I have a vector space sitting over an element little g and a vector space sitting over an element little h, then their tensor product is going to be sitting over the element g times h, where you use the group multiplication. So let me tell you a little bit more what you get here. If I look at what you assign to a circle, then this ends up being just a category, and it turns out that that category is the category of G add equivariant. So this, I can also say that this is a vector bundle over G. And here we get equivariant vector bundles. Over G, where this is the group acting via adjoint. And there's some more stuff in between. And I guess these were the things that Jacob talked about quite a lot last week. So So this looks like an easy construction that you certainly want to have around. I was very annoyed because this formalism, however fancy it is, does not accommodate for that example. There is no conformal net that, I mean, if G is a connected Lie group, then yes, you have the loop group conformal net. If G is a discrete finite group, then somehow this formalism isn't good enough to capture those examples. So given the situation, I ended up also wanting to replace conformal nets by something else. But before we go on, let's try to compare a bit those two things and see if we can line up a few of those things. Certainly, if I have an algebra and I want a category, there is a way of doing that. You can take the representation category of the algebra, and that will produce a category out of an algebra. So that's something you can do. A bimodule between von Neumann algebras is exactly the kind of thing that gives you a functor between the corresponding tensor categories. Because if I have a bimodule, I can I have a module, so an element of this category, and a bimodule. I can take the tensor product, and then I get a module for the other algebra. Well, here, as I said, Hilbert spaces of finite dimension and vector spaces, those are very much the same. So here it's the operation of tensoring over a bimodule. Tensor over A. If X is an AB bimodule, then tensor over A with X produces a B module. And so what I really wanted was a construction at the top level. I think that eats a conformal net and produces a tensor category. And that's what I'm going to talk about today. That's the subject of my talk. It's like tell you what these tensor categories are and what one can do with them. So I should comment a bit on the title of what I'm talking today. So I forgot to write the title. Let me write the title. I think now is a good moment to write the title. Okay, here's the title. The square root of a modular tensor category. Modular tensor categories, I've given some examples, even though I haven't really told you that they are modular categories. This one is, and the category that you assign to a circle in this story is a modular tensor category. So let's see. So if you just look at this formalism, to a circle you assign a category with no extra structure. A modular tensor category is a category with lots of extra structure. It's monoidal, it's actually braided, and then the braiding satisfies some non-degeneracy condition. Those pieces of structure are encoded by the fact that we have a number of functors corresponding to various cobordisms. For example, if I have the pair of tans that produces a monoidal structure on the category associated to a circle. If I notice that there is a diffeomorphism between the pair of pants and the pair of pants where I switch the two incoming circles, then that tells me that there's a braiding for that monodal structure. The fact that this diffeomorphism requires a choice of like either turning right or left tells me that this braiding is only a braiding and not a symmetry. It's not, doesn't square to the identity. And so this category here is the one that acquires all that extra structure from this formalism, and that is a modular tensor category. And actually one can say, so by the cobordism hypothesis, everything is determined by the top thing here. Once you know what you assign to a point, you know everything. So there is a name for the modular tensor category associated to an arbitrary tensor category, and that's called the Drinfeld double, also called the categorical center or Drinfeld center, but I'll call it the Drinfeld double. So this is and it's called double because in some there is some sense in which this category is twice as big as that category there. If you or maybe the size of this is the square of the size of the first. The size of this modular tensor category is the square of the size of that tensor category to begin with. How do you make specific the notion of size? What you need to do is you look at the collection of all simple objects. To each simple object you assign a notion of dimension, and then you take the sum over all simple objects of the squares of these dimensions. That's called the global dimension of the category, and then the global dimension of this guy here downstairs is the square of the global dimension of the guy upstairs. And so I didn't tell you what this is. I put a question mark there. But say in the case of loop groups, we know what this modular tensor category should be. It's the category of representations of the loop group at the fixed level, and then it's that category. And so the question of like finding a tensor category here, which was very much on the mind of people like Dan Fried or Konstantin Telemann, that's what I dubbed, well, trying to find the square root of the modular tensor category. So this is what we're after. So let me write I call it a pre-theorem. Pre-theorem just means that it's a theorem, but I haven't really checked all the details. And I realize that I haven't told you what conformal nets are, but I'll do that very soon. So given a conformal net, it is possible to associate to it a tensor category T sub the conformal net whose Drinfeld double is the category of representations of the conformal net. So let's see. Let me use blackboard bold D for the Drinfeld double. So the Drinfeld double of this tensor category is the representation category of the conformal net, which in the case of loop group nets is just the representation category of the loop group at a given level. So if you don't like conformal nets and you just like loop groups, you can say, as a corollary of this, associated to any loop group at a given level, there exists a tensor category whose Drinfeld double is the category of representations of the loop group. Yes?
Didn't you want it to be the representation category of the von Neumann algebra associated to the circle?
That's right. So it, in this case, for conformal nets that are fully dualizable, that ends up being the same thing. So there's a general definition given a conformal net of what you mean by the category representations of the conformal net, and that is slightly different from the notion of the representation category of the algebra associated to a circle. But if the net is fully dualizable, those two notions agree. In particular, for loop groups, if you believe that they are fully dualizable, then that agrees. But it looks difficult to find a square root of this modular tensor category. And the reason is that if you look at the simplest example of a loop group, which is the loop group of SU2 at level 1, then the representation category has two objects. So rep loops SU2 level 1 has two simple objects. That are both invertible, so they're both of dimension 1. And so the global dimension of this category is 2. I told you that it's the sum of the squares of the dimensions. It's 1 squared plus 1 squared. That's 2. So if we're looking for a tensor category whose global dimension is square root of 2. It's a tensor category, so in particular it has an object which is a unit. So we want an object of dimension 1, and we want an object, well, we want to do something with the remaining square root of 2 minus 1. In this context, dimensions are always positive numbers, and they can never be smaller than 1. Actually, an object whose dimension is smaller than 1 is 0. Then the next possible dimension is 1, and those are invertible objects. And then there's a beautiful result by Vaughan Jones that says that the set of possible values for a dimension are there's a discrete set of possible values. So 0, 1, square root of 2, and then there's an accumulation point until 2, and then from 2 on everything is allowed. But in part, this one would require to have an object of dimension square root of 2 minus 1, which is impossible. So that already sort of rules out the easy answer of this category being, again, one of these nice things with like finitely many objects. But if you allow for tensor categories that are big, that are no longer fusion categories, that have infinitely many objects, then this result about the global dimension breaks down, and it is possible to find big tensor categories whose Drinfeld double is relatively small. Examples of those have been written down in the in the case of abelian Chern-Simons theory. So Chern-Simons theory associated to a torus in the work of Fried, Hopkins, Leary, Telemann. They do write some examples of tensor categories with like infinitely many objects whose Drinfeld double is one of these. So for example, they would be able to treat this one. They know what to put up there. I mean, there's many choices of square roots. So what they write is different from what I have to propose. But anyways, it is possible to do it. So let's see. OK, so let me tell you about conformal nets. So a conformal net is a thing that will eat as input, is a functor. For conformal net, eats one manifold and produces von Neumann algebras. It's a covariant functor from one-dimensional manifolds, compact-oriented one-dimensional manifolds to von Neumann algebras. And it is such that, so let's call it A, it is such that if I have, it only allows you, it's only functorial with respect to embeddings. And if I have an embedding from a one manifold I into one manifold J, then, and well, let's assume that it's either orientation preserving or orientation reversing, then you get an algebra homomorphism if it's orientation preserving, and an algebra anti-homomorphism if it's orientation reversing. So this is the data of a conformal net. And let me also tell you what the conformal net is, which is associated to a loop group. So suppose I fix a compact, simply connected group, Lie group G, and the level then what the loop group net does, it takes the one manifold I, and it does a number of things to it. So first you form the version of the loop group which is modeled on I. Well, if I was a circle, I would look at all maps from I into G. So if I is a random manifold, I'm going to look at all maps from that manifold into G. If the manifold has some boundary, then I'm going to insist that the boundary goes to the base point of G. And I denote it like this. So this is now an infinite dimensional Lie group. You use this integer k to write down a central extension of that group that I denote by a tilde. That's now still a Lie group. I want an algebra, so let me take the group algebra of that guy. But that's by no means complete. A von Neumann algebra is some kind of complete topological algebra. So then you need to complete. That I denote by a big bar. So this is, let me comment. So this is a central extension. Depends on k. And that's a completion to make it into a von Neumann algebra. So it's like the group algebra of the loop group. And a representation of a conformal net it's a Hilbert space with actions. So I already gave you the sort of sloppy definition, which is to say it has an action of the von Neumann algebra associated to a circle. That happens to work out in the case of loop groups, but the thing that always works out is to say that you have actions. So S1 is the standard circle, and you look at all submanifolds, but not the whole thing, and then look at things that have actions of all these submanifolds and that are compatible with restrictions. So if I restrict to a smaller interval, I want it to be given by. The action should be the restriction. So there is a monodal structure on the category of representations of any conformal net. And that goes as follows. Suppose that I have a representation H and a representation K. So H has actions of A of I for any interval I that is contained in this circle that I drew around H. And K has actions of A of I for any interval I that is contained inside this circle that I drew around K. So we concentrate on those two halves. And then you have this algebra acting on the left on K, and the same algebra but for the interval with opposite orientation acting on the left on H. Well, suppose I identify this with that using this orientation reversing map, then that identifies one algebra with the opposite of the algebra of the other. So this algebra acts on the left on K and acts on the right on H. Then you take the tensor product over that von Neumann algebra. Another way of saying it is as follows. So take another way of saying this is as follows, is to say I look at the standard circle, I cut it in two, I parameterize this half by 0, 1, and that half also by 0, 1, and that embeds the category representations of the conformal net into the category of bimodules for the algebra associated to this. And that one now has an obvious monodal structure. And the monodal structure here is inherited from the one there. So it's useful to do that in a slightly more coordinate-independent way. Instead of talking about the standard circle, S1, to talk about an arbitrary manifold which happens to be diffeomorphic to S1, but I don't want to use any chosen diffeomorphism to S1 in order to formulate definitions. So S is my manifold, and A is the conformal net, and S sector of A is a Hilbert space H with actions of So this is really the same thing as that, except that I replaced S1, which is denoted in the standard circle, by S, which denotes another manifold. And as I told you in the case of conformal nets coming from loop groups, this is the same thing as just looking at a Hilbert space with an action of one algebra. So now let's do this. I is now an interval. Let's take it to be the standard interval for definiteness. So an I sector is a Hilbert space equipped with actions of, well, for any subinterval of 0, 1, but not the whole thing, I have an action. For the whole thing, I do not require to have an action. There's a similar model structure on the category of I sectors. So here's how it works. Well, it's just like this. So I'm going to look at my interval I, which is here. And I'm going to choose two embeddings, one which is orientation preserving, the other one which is orientation reversing. So let's embed 0, 1/2 into I. I is 0, 1, so I embed it like this in the obvious way. And let's embed it in the other direction in an orientation reversing way. So by the map, x goes to 1 minus x. And that provides an embedding of the category of I sectors of A into the category of bimodules for the algebra associated to that smaller interval. Same thing as here, except now I do it on an interval. So that is the category that I propose here at the top. So maybe it's worthwhile spelling out what this means in the case of loop groups, because I mean, there is a way of spelling out what this means without ever talking about von Neumann algebras, so let's do that. So we fix G, simple Lie group, and K a level. So an I-sector is, well, it's a Hilbert space with a bunch of actions. So it's a representation of the based loop group of G. So let's see, what did I say here? So we're looking at based maps from the interval into G. Well, our interval now is 0, 1. So base map from 0, 1 into G, that's the whole omega G. And here I explicitly excluded the case where the thing is the whole interval. And there I'm saying that actually you can recover, as far as just the loop group is concerned, you can recover it. You will not be able to extend it, this representation, to the von Neumann algebra associated to that. But this is something that you do get, the representation of this guy. Centrally extended by the co-cycle corresponding to K. And if I wanted to be specific, I should say something like smooth loop groups. Such that so maybe I should say specifically omega G is maps. So send both endpoints to the element of G, such that for every J which is strictly contained in here, if you look at the restriction of that representation to the set of loops supported in J, so the set of gamma, so these are maps from 0, 1 to G, which are supported in J, such that the support of gamma is contained in J. So everything outside of J goes to the identity element of G. Is equivalent to a representation coming maybe I should say is equivalent to the restriction of a positive energy representation of the loop group, of the free loop group. So there's no condition for the whole interval, and then there's some conditions for the smaller intervals. So to be equivalent to the restriction, that's essentially the same thing as to say that this representation of this group extends to the correct von Neumann algebra. And if I don't have this restriction, then I could extend to another von Neumann algebra. So no condition on the von Neumann algebra generated by the whole thing, but yes, there's conditions about the von Neumann algebras generated by the small intervals. That's right. So I want to propose that as the tensor category associated by Chern-Simons theory to a point. So now
this condition, do you require somehow that both endpoints do not belong to I? Or
no, as I wrote it. So it's I allow things that go to one endpoint or to go to the other endpoint, but not to both endpoints. So maybe I'll just make some comments about Drinfeld centers. So that category there, that category is huge. You should think of it as having roughly the same size as the category of, well, fixed von Neumann algebra, say fixed type 3 factor. It has roughly the same size as the category of all bimodules for a fixed type 3 factor. So there's no way, no hope of ever understanding what all the objects in that category are. The Drinfeld center, what's an element of the Drinfeld double I've been calling it. The Drinfeld double, what's an element in this Drinfeld double? Well, it is the data of an object of the category and a braiding of that object with any other object. So I told you that there's no hope of ever understanding what the objects in here are. So this would imply that there's no hope of ever understanding what it means to have a half braiding with all the other objects, because there's way too many. And so what one needs to do is to actually put a grain of salt on the definition of Drinfeld double, to modify the meaning of that in order to make this theorem be true. So one needs to view this as a topological category. And by topological category, I mean that, well, there's a topology. That's what it means. But what does it mean? I don't mean that there's a topology on the set of morphisms. I mean, that also is true. But what I really want is that there's a topology on the set of objects. More precisely, there is a notion of family of objects over any parameter space that you choose. So to be precise, this should be viewed as a stack fibered in tensor categories over the category of all topological spaces. And that needs to be taken into account in the definition of the Drinfeld double. You need to ask for the braiding to be continuous. And once you ask that, then it's possible to actually control this thing, because even though the collection of all I sectors up to isomorphism is completely out of hand, there exists a single I sector which is whose closure is the whole thing. So there exists a single I sector such that if I take it and everything that's isomorphic to it, then I take the closure, then I have everything. So this is a way of getting a control on this category. In the case of the category of all bimodules for a particular von Neumann algebra, there's a similar phenomenon. If I look at, so if A is my von Neumann algebra and I look at all bimodules for A, there is in it those bimodules that come from modules of A tensor A up. And those are dense inside everything else. So anyways, so I just presented you this definition. And I guess I have to stop here.
Any questions? That last thing you mentioned, instead of what you said, can you kind of view this tensor category as some sort of internal to spaces?
Yes, you can do that. Yes. This category here of all bimodules can be replaced by a category internal in spaces where the objects are no longer bimodules. I mean, there's a class of bimodules. There's no way of ever putting a topology on a class of things. So if I call this straight A, then if I have an algebra homomorphism from A into A, then you can get a bimodule out of that algebra homomorphism. Namely, take the identity bimodule and twist one of the actions by that homomorphism. So you can take those algebra homomorphisms as your objects. And now there's a set of them, and now that set comes with a nice topology. The Hagerup U topology, which is the one that I use up there. And actually, that's exactly the way I do it in that case. Is to sort of actually say it comes from a category in top.
Does that think interesting happen if G is a finite group?
Well, you recover the old story. So the way to say it that works. That's right. So I said it in a way that does not. Let me say it in a way that where the two cases are treated at the same time. So I'm looking not at representations of a group, but at vector bundles on a moduli space. And the moduli space that is relevant here, and that I learned from Graham Siegel, is okay. Let's see here is a vector bundle on the moduli space of principal G bundles over 0, 1 trivialized at 0 and at 1. So if you take a connected Lie group, then every vector bundle on the moduli, every vector bundle of the moduli space of G bundles over 0, 1 trivialized at 0, 1 is equivalent to every other one. And so we only have one object, and that object has a certain group of automorphisms, and the group of automorphisms is the base loop group, because I fixed the two trivializations. If G is a finite group, then you have the opposite phenomenon, that there's no automorphisms of such a thing. If I have a trivialization that at one endpoint, that automatically trivializes the whole thing, but now I have a second trivialization at the other endpoint, so that trivializes it again, and what you're left with is an element of G. So we have a vector bundle on the underlying set of G. So G-graded vector bundles. And that was exactly what I had here on the board before that. So it's an example of this. Yeah?
So saying it that way, is it true that this thing has a kind of rigidity, so that are there duals for objects in this monoidal category?
This monoidal category is big. You certainly don't expect everything to have a dual in it. Some objects will be dualizable in there. It's just like in the category of all bimodules for a fixed von Neumann algebra. Well, some bimodules are dualizable, some aren't. So, but for those that are dualizable, then there's a good theory of duals.
What's the identity sector like? The unit object for the monoidal structure?
In there, so you can see it here. So I said that an I sector gets embedded in the category of bimodules for this algebra. So it's the identity bimodule with its I sector structure.
So you've been making the not being equal in the I sector and in the component S has been pointed out. So is there anything you can say about like the base loop space, path space, free loop space vibration?
Okay.
In relation to that?
And in relation to the vibration, base loops, paths, and free loops. Sorry, the vibration has G as the fiber, the path space, and then the base loops. Or I guess there's a couple of variants of that fibration. Yeah, I'm not quite sure what to say about it. I mean, you could imagine looking at that category would have only a trivialization on one end, and ask if there is anything reasonable to say about it. And the answer is I don't have anything to say about it. So yeah, I'm sorry.
What is the home of this whole construction? Somewhat confused. So you start with a fully dualizable object in the three categories somehow. Then you construct something where at the moment I don't see where it lives. And then, I mean, we know that we have on the left, very left, we have the construction of the T group D. So do you say that there's some intermediate category over which this construction factorizes? Or so where does this little thing live and where can I look at it?
So a very good question. The question is, well, these things, there is a three category of them, and those, at least before I told you what this three category is, maybe you thought that there is a good three category of them, but then I told you what it is and it became all confusing. Well, the wish is that there will be a three category whose objects are things that, for which this is an example. And in that big three category, there should be a fully dualizable object. So
do you then think that you construct the equivalence of those three categories in some four categories?
So the picture that I have in mind is that there's a three category of conformal nets, which is quite okay, except it just misses a few objects. It misses the objects that are there for example, to do finite group Chern-Simons theory, and that there is a fully faithful embedding into another three category that has a few more objects. That's what I would like to happen. Well, then the question is, well, can one formulate a definition, an abstract definition, such that this is an instance of that definition? And well, I can make a guess. So the guess would be that I look at well, topologized tensor categories, meaning tensor categories that are actually also where it makes sense to talk about families of objects, that it is possible to embed inside the category of bimodules for a von Neumann algebra. So the analogy that I have in mind is that it's an analogy with the definition of von Neumann algebra itself. So a von Neumann algebra is an algebra that it is possible to embed in the category of all bounded operators on a Hilbert space, without chosen embedding, but it is possible to embed it. So now I will replace this by the tensor category of all bimodules of a given big von Neumann algebra. And I would say that the kind of objects that I consider are abstract tensor categories that it is possible to embed as a closed thing inside here. Meaning whenever I have a family of objects that are indexed, let's say, by 0, 1, and then all the objects from 0 to not including 1 are in that image, then I would require that the endpoint also is in the image. And I would think, so I think of this as a categorification of the notion of von Neumann algebra. But right now I only have a few examples, so it's maybe a bit premature to say that this is a correct definition.
Right, no more questions. Let's thank the speaker again.